Hi everyone, and welcome to another episode of AI Talks. And today we have a special edition specifically talking about reinforcement learning.
Hey, my name's Akanksha Malik and I'm from Melbourne.
Excellent Sami in Belgium.
Hi, I'm Alan Smith.
Hi, I'm Amy.
Hey, I'm Kat. I come from Spain.
I'm Prasant from California.
大家好，我是卢建辉。
I'm Farkas from Australia.
Hi, I'm Jennifer Marsman from the United States.
Hi, I'm Akita Gupta from India.
Hi, I'm Matthew Renton from the USA.
I'm Joe Spizak from California. Hi, Midi Eddie Daoud from Africana.
Hi, I'm Ana Falana.
Merhaba, ben Türkiye'den Daron Yönden.
Hi. Hi. Hi.
Hi.
Hi.
Hi.
Hi, so all welcome back. As I said before, it's a special edition today. So some special things also. We have not only one guest, but we have two. Welcome, Eve and Alan.
Hi.
Hi, good evening.
How are you guys doing?
It's really nice to be here.
Yeah.
Can you introduce yourself? Let's start women first. Eve, who are you?
Yes,
what do you do in your daily life?
So first of all, an AI MVP, and in full time, I'm working at Laerdal. It's a company that is based in Norway, but it has offices all around the world. The aim of this company is to save more lives by providing trainings inside classroom or online as well for nurses and doctors, so they can practice how to be better at saving lives. I am a data analyst, data scientist, and software engineer at this place right now. And on the side, I enjoy writing articles and talk about AI stuff at different conferences or meetups or other community events. So I'm very happy that I can be here today.
Cool, thank you, Eve. And Alan, you are in your server center, I see.
Yeah. Name is Alan Smith. I'm from the north of England, but I'm based in Stockholm, Sweden. I'm a really long time MVP. I was first awarded an MVP in 2005 as a BizTalk server MVP. And I've kind of followed through being an integration MVP and then moving into the Azure when Azure seems to be an exciting technology to work with. So I'm currently an Azure MVP, and I'm spending a lot of my time looking at the artificial intelligence and machine learning technologies that are available on the Microsoft platform. So I spend time looking at custom vision is probably my favorite service. I also look a lot with the cognitive services, computer vision, and things like that, and also the machine learning studio. And I'm also learning Python with a view to learning more about machine learning, because that seems to be what many people are working with. So I'm looking at Python and TensorFlow and Keras and all of these exciting technologies. I work a lot with training, so I'm a Pluralsight author. I also deliver classroom training courses and courses for companies. And like Eve, I like to get around, used to speak at a lot of conferences, but now everything's going online. And I've also been involved in organizing the Cloud Burst conference and the AI Burst conference, which we did have scheduled for this year, but we're planning on hopefully scheduling and running next year. And the AI Burst is part of the global AI community.
Cool. Thanks for that. So, as we said today, we're going to talk about reinforcement learning. If I'm correct, Alan, you will give us a theoretical overview of what reinforcement learning is, and then Eve will give us a practical example with some new services and tools that are there, right?
Yes.
So with this, I will give the platform to Alan.
Great, thank you very much for that. So I'm going to start off talking a bit about reinforcement learning and a bit about the theory on reinforcement learning and some of the work or experiments, as we call them, I've been doing with reinforcement learning technologies. A bit about my intro. As I mentioned, I've mentioned most of that. I also do have a YouTube channel, which I'll give you a link to. Some of the video content from this presentation is coming from my YouTube channel. I've also got some videos up there of some of the work that I've been doing with AI. So basically, with reinforcement learning, more focusing on, instead of starting with a large amount of data with training data and test data and training network based on answers that we already know. We're going to be using artificial intelligence to basically explore an environment. And in many cases, this environment is some kind of physics simulation, or it's a game. It's something that we can kind of visualize in the form of a video, where we're going to be providing inputs and we're going to be getting outputs for that environment. So, you know, an environment could be a driving game. It could be like a Lunar Lander game. But all of these environments basically have something in common. They will provide a state, and the state will be kind of a description of the environment at a current point in time. So it will be, you know, if it's a chessboard, you know, the state of a chessboard is going to be the positions of all of the pieces. The state of a Pac-Man game is going to be where all of the dots are, where the Pac-Man is, and where all of the ghosts are as they're driving, you know, going around, trying to capture the Pac-Man and so on. So state is going to be description of the game. We've also got some kind of action that we can take. And in a game, this is going to be, you know, the keyboard or the joystick or the actual inputs, the move that you decide to make. If you're playing a chess game, you know, what kind of action you're going to take. And the action is going to make ensure that the game is going to transition to another state. You know, if you make a move on the chessboard, then the state is going to be different. You're going to affect that state. And affecting the state on the game could have a positive effect. If you're playing chess, you could take somebody's queen, and that would basically mean that there will be some kind of reward. The actual, you know, score of your position, the way you evaluate your position, is going to be increased by taking that particular action and putting the game into a different state. So with reinforcement learning, we're going to be working with an AI, some kind of algorithm that's going to drive this environment, and we call this this algorithm, which is encapsulated within an agent. And the algorithm is basically going to be fed the game state. The algorithm is going to decide, or the agent is going to decide what action to take based on that state. And that is going to result in the environment going into a new state and generating a reward, which is fed back into the agent again. So we kind of get this reinforcement or this feedback process. If you kind of work with engineering and looked at feedback loops, it's a kind of feedback loop whereby we're going to take an action based on the state and the reward. And the idea is that the agent is going to learn from you know, making these different decisions based on the actual state of the game. So when we think about the state, we're going to be working with different environments, and we need to think about, you know, what is going to be the input state. I like physics. I was kind of a physics geek at school. So anything where you've got physics involved, where you've got, you know, something that's measured in meters per second, you've got altitude, you've got the horizontal speed, you've got the vertical speed. And in a scenario like a Lunar Lander game, you could say, well, the state of the game is going to be, you know, the position and the velocity of the actual Lunar Lander and information about the environment that it's in, you know, how much fuel it's got left and so on. And based on these actual values, we're going to make a decision about whether to rotate right, rotate left, or, you know, how much thrust to send to the engine, as we're going to be learning to land. Other games, there's a lot of these Atari simulations based on the old, you know, Atari console that came out in the 80s. And this is one of the Pac-Man games. Now, because it's a pretty low resolution screen, when we're actually simulating in these Atari games, what we take is the actual, you know, bitmap image of the screen, which is basically showing, you know, where the Pac-Man is, where the ghosts are, and based on these actual pixels, we're going to, you know, take some action to move up, move down, move right, and move left. Now, there's a really good advantage to actually using the screen bitmap image instead of using the actual, you know, physics from the Lunar Landing game. If I'm building my, you know, the inputs on my agent based on altitude, horizontal speed, vertical speed, it's kind of limited in the types of simulations that we're building. However, if our agent is able to take in a bitmap and be able to send, you know, the joystick outputs, it's going to be able to learn how to play a vast majority of the Atari games, because the input is going to be the same, the actual state is going to be the same, it's going to be a bitmap, and the action is going to be, you know, the moving of an actual joystick controller, rather than, you know, setting the actual, you know, thrust percentage on a rocket engine, or rotating right or rotating left and so on. So it can be a good advantage to use the actual screen bitmap. However, when we get onto to complex simulations, it can be a real challenge to actually use the screen bitmap. If we look how much gaming has evolved, and especially game graphics with the new consoles, you know, having things like ray tracing in the actual consoles and delivering, you know, the game output in 4K sometimes 8K resolutions, it's going to be really challenging to actually process these types of bitmap inputs and treat that as the actual game state. You can see on the screen that there's all kinds of stuff. You've got the road cones, you've got all these kind of visual lens flare effects, kind of distorting things, and you've got the cones. You've also got how is the AI going to understand what to do in this particular situation? We can tell because there's a driving line and because of those small road cones that we're going to be making a left turn here, and we're going to have to turn left around that corner. However, looking at the image, depending on how you interpret that, you could say, well, going in a straight line is going to be driving down the road as well. That's maybe an option that we could take. And how do we differentiate between a left turn and going straight? How do we know when to use what? Now, the clue in this is the actual driving line. You can see there's kind of this cyan color driving line that's highlighted. And in some cases, and I've been doing this when I've been, working with reinforcement learning on the Forza game, what I've done is actually done some image processing on the actual game image itself. So I take the frame for the game, I do some filtering with that to extract the actual pixels for the actual that make up the driving line. I'm lowering the resolution as well, and also doing an actual tilt on the image. So this is kind of generating a top-down view on the track rather than the view at the angle there, and being able to feed in this as the actual game, this process state into the algorithm. Then the algorithm's got a much less signal to noise ratio on how it's going to be processing that particular input there. Also, one thing I have experimented a bit with is looking at the, how we can use other neural networks. Here we're using the custom vision service, which I've trained on frames from, the Forza driving game to be able to identify other cars within the Forza driving game. So it's basically identifying and detecting these other cars, and you can basically react, hopefully, to the positions on the actual screen. So here we're using an actual, trained neural network, a vision network. What's it called, convolutional neural network, to actually find the position of the cars, and then we're using reinforcement learning based on the outputs from that convolutional neural network. So it's great fun, and if you want to do all of this kind of stuff, there's many companies and also research and hobby projects where you can look at working with custom driving algorithms and so on. There's a lot of great research and development going on in there. As far as the actions are going to be concerning, this is going to be what we actually feed in to the environment to be able to make it transition to its state. So it could be simulating key presses if it's a game. It could be simulating the joystick as we're doing with the Atari simulations. And with the driving simulation, it could be making inputs like a certain amount to turn the wheel and so on. And then we get on to the reward. How do we start to think about classifying the rewards? In the Lunar Lander, what you could say is, well, the aim of the game is to actually land the Lunar Lander without crashing. And you could also take a numeric reward and say, well, what is if we do crash? How fast did we crash? Because obviously, crashing at a slower speed is an improvement on crashing at a faster speed. And if we can, decrease slowly over the iterations the speed at which we're crashing and crash slower and slower and slower, eventually we're going to be able to land without actually destroying the Lunar Lander. So that's one way we can think about the reward. Instead of being a score where the higher number is better, the lower number, the actual impact velocity when you actually hit the ground, that we want to be able to achieve the lowest value. And it's something that we can compare numerically. For the Atari games, the score could be the option that we go for. What is the highest score that we could achieve? It could also be clearing eating the most number of dots. That could be a better progression, because actually clearing those and clearing the screen could be better than getting a higher score and not clearing the screen. So you can decide on what the actual reward is going to be. This jumped in a bit out of sequence, but for the driving game, the reward that I was using when I was playing around with Forza was how far did the car actually drive, and the AIs that were driving the furthest would basically that would classify as being the best reward. So I'm going to jump into a couple of examples of the kind of AIs I've been working with. The first one is a driving game, and we've seen here that the state is going to be using the actual screen resolution, but then doing some processing on that to be able to actually produce an actual process state, and then using the input as being the actual steering, how we actually steer the car. On this example, what I'd done is I'd set the car to run at a constant speed. I hadn't run with the acceleration. I basically just controlling the steering based on the actual state that we see there. And I've got a video about how that evolution took place a bit later on. We also, when we're thinking about gaming AI, this was a really interesting sort of a YouTube presentation that I saw when I was researching this, is as humans, we kind of make a lot of assumptions about how we're going to play a game. We tend to learn very, very quickly because of our human experience. So you can tell by looking at this actual game, we've got a lot of prior knowledge. We can probably tell that the player is going to be this guy who stood at the bottom of the screen. Because that's typically where you start, and typically the player is going to look like that. We've got these purple ghosts, they look evil. You've got these spikes, which is probably not that great to stand on. And you've got various platforms that you can jump onto, and you've got a thing that looks like a ladder. And we recognize it as a ladder, because we've been, interacting in our environment and learning a lot about our environment. However, computers probably won't see it like that. They won't have all of this prior knowledge. So this is maybe more like what the computer sees. They're seeing, various different colored blobs, and it's got to kind of figure out which blob is the player, and pressing, certain buttons or sending certain input is going to trigger certain blobs. And what about the pink blob? Is that a nice blob? Is it good to jump on the pink blob? Is it good to jump on the green blob? And it's going to learn all of this through learning. And it may, kind of look like this as well to the computer, where it's, not real much differentiation about what's what. It's just looking at this kind of map of pixels, this mess of pixels, trying to, increase the score by making various inputs based on, how these pixels change. There is a really interesting link if you look up for this, where they talk about reinforcement learning, where you can actually play the games in this form and in this form, and basically see, how the machine is seeing the game and see how it affects the way that you play based on your prior knowledge. And there's a lot of good research that's taken place on that. So moving on to a couple of the examples. The first one I'm going to look at is something that I built, which is one of my first sort of forays into looking at working with machine learning. I'm just hoping that this doesn't deafen you because the rockets make a lot of noise. But this was in Unity, and basically using evolutionary learning. And that's kind of inspired by the Falcon Heavy launches that were taking place around the same time, where here we've got a bunch of rockets, and they're basically landing. And what I'm doing here is basically treating the reward that we're going to give as being the actual lowest landing speed. So most of the rockets crash, but some of them crash slower than others. And eventually, if they land at a certain speed, below a certain speed threshold, they're going to survive it without crashing. And what we're doing here is basically going through generation after generation, just basically reinforcing the learning of these rockets to be able to learn and be able to minimize that actual impact speed. And you can see that after running through a few of these iterations, we've actually managed to land these 25 rockets successfully there. Another example I'm going to look at, this is another of the early experiments I looked at, was the 2D driving game. And what I was doing here was I kind of built this 2D driving simulator when I was playing around with gaming physics, and just basically learning how a 2D car will work on track. And what I was using is using this simulator to actually, for the environment for reinforcement learning. So I'll just see if I can drop this onto my presentation screen. So what we're doing here is we're basically starting with, I think, 50 cars in each batch. And these are basically making random decisions. They're basically attempting to learn to drive around this track. And the reward that I'm giving them is the number of pixels in distance that they have driven. So the first generation has got 543 pixels. Hopefully, subsequent generations may improve on that. It all starts off with random numbers. They're randomly seeded. So it could take a few iterations before we do get an improvement. But hopefully, we should see that improvement coming through eventually. It's looking like that one did actually get further. So that one's got 906 now on the fourth generation. And I can mess around with the environment. I can be really cruel because here at the top, I've got a slider which controls the friction. So they're currently driving. They've got a lot of friction. But if I go like this, they're going to be driving on ice. And that's going to mean that they're probably going to slide off and crash, taking their current behavior. But, are they going to evolve and learn, how to drive on ice? This one does seem to be actually making that actual correctly. So I'll just drop onto the next generation. We should see hopefully them a lot sliding off and crashing when they attempt to drive with zero friction. So you can see that it's not going too great on the driving, but they should hopefully evolve because the environment has now changed to be an icy environment, and they should hopefully evolve to be able to, learn how to drive on a more icy surface. So those couple of examples I was looking at, they were basically focusing on environments I built myself, in that, I hadn't worked with any kind of a framework. I just basically, built a very simple simulation, and then built some, evolutionary learning. It was kind of running in the same process, and there's no kind of standardized way of being able to interface with this. So what we're going to look at is a couple of products or technologies that we can leverage, and this is what Eva's going to be talking about later on when we look at the Microsoft technologies and how we can use this within Azure Machine Learning. One of the technologies is OpenAI Gym. OpenAI Gym is basically a toolkit that provides us with a number of environments that we can use for being able to run and develop our own machine learning models. So, one of the environments that we've got is something called cart pole. So this is basically, if you've got a pen and you want to balance it on your finger, this is something that is hard to do for humans. And this kind of simulates this in 2 dimensions with a very simple physics engine. And the idea is that, the reward is going to be how long we can actually balance the actual pole and keep the pole upright without the pole going, more than a certain angle. The state is going to be the position of the cart and the angle of the pole, and the actual inputs that we can make is to the actual velocity or the force that we apply on the actual cart to move it left or move it right. So the idea is that we're going to be moving this to keep things balanced, and we increase the reward. We increase the time that the pole is going to stay up there, and that's going to be the reward. And hopefully our AI should be able to learn, how to actually balance the actual pole onto the cart. That's one of the most simple ones. We've also got these nice environments. They use a couple of physics engines. I think Box2D is one of them, and they've got another physics engine here, which is doing a 3D simulation of this creature. And the idea here is that we can, make bipeds or quadrupeds that can basically learn to walk and learn a walking sequence, which is a lot more advanced than the cart pole scenario. It's another scenario that we can look at that's provided in a gym environment. We've also got the Lunar Lander, a bit like my landing rockets, whereas here they can also move left and right as well. And you've got the option there to be able to provide those inputs and look at the outputs there. I'm not sure if this is based on the actual physics or based on the screen bitmaps. I'm guessing it's going to be based on the physics here. And then we've got the Atari games. This is Space Invaders. I was actually, think about 8 or 9 years old when Space Invaders was actually released. So I remember seeing this in the arcades when it was first released. And we've got this Atari games. We've got the basically game ROMs, and we can basically use the algorithms to use the technologies to be able to actually evolve and be able to play these Atari games. And you have got the option to be able to run these actual Atari game simulations. A lot of work has been done on that. So one of the things that's great about using the OpenAI Gym is it provides a common interface to the environment, so a common interface between the actual agents and the environment, which means that we can basically leverage this in many different scenarios. So we've got a number of different environments that we can specify there, and we've got a number of different agents as well. And what the gym interface provides is the observation space, which is going to be providing the game state, the action space, which is defining the actions that we can invoke on the environment, and then it's providing these various methods, the step method to actually go to the next step and execute that action and give me the actual next observation. The actual render, which is going to be able to generate an actual bitmap frame of that actual the game state, so we can actually play this as an animation if we want to, and also reset if we want to end and basically reset and put the pole back up at the top, or reset the game back to the state that it was previously. We can basically fire off a reset function. And this means that we can basically plug in our own agents and plug in different environments into this OpenAI Gym configuration, and we can basically define our own environments fairly easily. And this is an example of the actual Python code that forms a custom environment. We're specifying a class which is deriving from the gym environment, and then we're defining the action space, the observation space, and we provide implementations for step, reset, and render based on our particular environment. So you can play around with the gym stuff without actually having to work with the Azure Machine Learning. And here's a very simple Python example that's using the cart pole, I think. If I can just drop this. onto my screen. I've got multiple screens here. So this is just basically providing some cart pole simulations here. And what I'm doing is you normally don't render on every frame, because this really slows down how fast the actual machine learning can run. It runs about 1,000 times faster, I think, if you're not actually rendering all the frames. So this is nice to actually see the animation there. And that's one of the cart pole ones. Another one that's quite a common scenario is the mountain car simulation, where we've basically got a car that you've got to drive up a mountain, and it's not possible to drive the car up the mountain by just using actual, the force of the engine straight away. What you've got to do is you've got to basically back the car and then go forwards and back and forwards to actually get up to reach the goal. So the AI basically has to learn that it's got to move back and move forwards and learn the actual combinations of that. So there's a couple of simple basic simulations that is really useful to look through if you want to just understand a bit about how the different algorithms work and how you can actually work with the reinforcement learning. So the other technologies that we're going to be mentioning, I'll mention a bit about this, which is Ray, which is a way of being able to run distributed applications in a Python environment. And then built on top of Ray, we have the RLib, the RL lib, which is a way of being able to run reinforcement at scale. And the idea here is that we're going to be leveraging Azure and leveraging Azure Machine Learning to actually, run this in an actual cloud-based environment that we can provision and we can basically tear down when we need to. If you look at the actual prices, how much it costs to buy a machine learning workstation with a number of GPU cards in, it gets scary expensive on how much these machines cost. If you look at the cost on how much it costs per month to rent one of these GPU machines in Azure, this is also really scary when you look at those pricing. However, if you look at the per hour pricing on being able to rent one of these machines, it starts to become affordable in that, you can run a really, really big machine for a few hours to be able to, run a machine learning experiment and then just tear down this environment and stop paying for it. So the per hour pricing does work out very good. Also, it's the same price to run, one machine for 100 hours is to run 100 machines for 1 hour. And running 100 machines for 1 hour, you get your results back much quicker than running one machine for 100 hours. It's like 1 hour instead of 4 days. So leveraging the clusters, using the machine learning and using this technology allows us now to be able to do these reinforcement learning tasks up in Microsoft Azure. So that's all I was going to mention on the reinforcement learning. We're going to now be looking at the main exciting part of this, which is looking at what Microsoft Azure is doing in the gaming world using these technologies.
That was really exciting, Alan. So we cannot hear you, Sammy, actually.
So Eve, sorry, my mic was muted. I gave the platform now to you. You can go on.
Yeah, hi. So, do you want me to go ahead?
Yeah, you share your screen and share.
Okay, cool. So, hi everyone. I'm very happy that I can be here as well. And I think we got an awesome intro from Alan. And I was actually smiling at it a lot because I'm not a game developer, but from now on I might start and looking into it because some cool stuff is available for game developers nowadays, and it's really cool to go and look into that. And Microsoft made an amazing history in machine learning and artificial intelligence. And they proudly announced the preview of reinforcement learning that is available on Azure Machine Learning at the Build conference this year. And Microsoft applies machine learning to improve many of their products and services. They also use it, for example, for the suggestions made in the Office services. So I want to refer back for a moment to what is reinforcement learning and keep it in very short sentences. So it is a machine learning paradigm which trains the policy of the agent so that it can make a sequence of decisions. And the aim of the agent is to output actions according to the observations it makes about its environment. And these actions then lead to more observations and rewards. And this training involves numerous trial and error runs as the agent interacts with this environment. And in each iteration, it is able to improve this policy. And this learning approach, as you could see, became very popular in the recent years since these agents perform complex tasks really well thanks to reinforcement learning. This also causing real breakthroughs in the field of AI. And also there are many use cases in the world which uses this technology in the areas such as robotics, chemistry, and the focus of this session, as we already talked about, is game development. In the context of video games, the agent that takes actions or performs a behavior is the game agent. And you can think of a character or a bot in a game that has to understand the state of the game. It has to know where are the players. And then based on this observation, it should make a decision based on the situation of the game. And in reinforcement learning, decisions are driven by rewards, as we talked about this before. And in the game, it could be provided as a high score or a new level for reaching a specific goal. And the cool thing about the gaming context is that the policy of the agent is trained under the pressure of the game. For example, it could learn what to do if it is getting attacked or how to behave in order to reach a specific goal. So if you're ready to get started with reinforcement learning, you can check out the sample notebooks to train an agent to, for example, like this guy here that tries to navigate through a lava maze in Minecraft. And this is also using Azure Machine Learning. So the goal of this agent is to reach the blue tiles while navigating through this maze by walking only on solid tiles. And this agent might fall into the lava, and in this case, it has to start it over. And these maps are generated randomly, and this is why the agent has to learn how to generalize and adapt. If you want, you can take a look at the sample notebooks that you can find on the link defined over there. But I will share you these resources later on too. So now let me introduce you to the new stuff that is available. I hope it won't have noise because we don't want voices for that. So Microsoft Research worked together with Ninja Theory to explore new possibilities of reinforcement learning in gaming. And Project Paidia, it has been announced on the 3rd of August at Games Tech Live, and the state-of-the-art AI agents used Bleeding Edge as a research environment. And the aim of these researches is not to build an agent that is able to beat humans, just like it could do with, this very famous chess player has been beaten by an AI agent. And the aim now is to provide game developers tools to make them able to apply reinforcement learning while building exciting games for their players. So the new reinforcement learning support in Azure Machine Learning, this provides scalability while training to CPU or GPU-enabled virtual machines with machine learning compute clusters that are also able to automatically provision, manage, and scale these virtual machines. You can also use single agent, just like we've seen with the Minecraft game, where you basically train one agent. Or you can use multi-agent reinforcement learning for the different training scenarios. You can also use different gaming environments, for example, OpenAI Gym that you have already heard about. Thank you, Len, again. You can also build your models with TensorFlow or PyTorch, and it also has support on Onyx too. Then you're also able to track your experiments and monitor all the runs, all the iterations. And Azure provides, numerous AI solutions that is available for you when you want to build and run and grow your games. So you can accelerate your games with AI and machine learning, and you can provide more realistic worlds and challenges for your players. So for this session, I prepared you the new Project Paidia that has been announced on the 3rd of August. And this is now a multi-agent scenario because we are training, at least in this case, 3 agents. Because the scenario is the following. The blue circles are the agents, and they start spreading around, and they observe the environment. And while they try to find these black landmarks. So these black circles are the landmarks. And that's what the blue circles have to find. So these agents will get rewarded if they find the landmarks without overlapping while spreading around. And for this, we use OpenAI Jim's particle environment within Azure Machine Learning. So I think I'm ready to switch over to the demo so I can show you around what you have to do to make this happen. So I'm going to switch back to my demo, and all you need to do to get started is to have an Azure subscription. You also have to set up a resource group for yourself where you have to create an Azure Machine Learning workspace and also a computation cluster inside this specific resource group. Then also a compute target should be generated. And if you go to launch now, your workspace is starting up. And if you go to the compute menu over there, you can create a new compute. Now I already have one, and this is what I'm going to use. So just go ahead and show you the notebook. And I want you to remember that I'll share everything with you later on, so you will get the code also and all the documentation available for this session. So I just want to note here that this is not the only file needed for this project. We also have this files folder where we have Python files inside holding very important methods in it. But right now I want to focus on how easily you can put together a scenario where we actually train the agents, actually 3 agents that are able to collaborate with the environment and learn from it, and then find their place without, overlapping. Because we don't want to go too close to each other. We learned this already. Now they have to learn it also. All right. So when you get started in the notebook environment, it's a good idea to update some packages for yourself, and then we can also return the SDK version. I can see some errors, but no worries. So the idea is that we can see the SDK version. So if you want to debug something, then you can see it here. Then you also need to define your tenant, your Azure tenant you want to use. And if you want to specify that, you can just go to the Azure portal. And if you go to Azure Active Directory, there you can see and the tenant information that is here. All right. Okay. Now I'm going to create now. I want to connect to my workspace that I just created. This is the workspace that I created, and I specify that, okay, this is called EveML. Then I specify my subscription ID, and that the resource group is MSLearn. And then when everything is succeeded, it just returns the information. If you want to find your subscription ID, you can also find it on the Azure portal if you go to the subscriptions menu. So now we can see the connection was succeeded. And the next step is to create a new experiment. It's really cool to have an experiment because this is where we're going to see the run details inside the Azure Machine Learning environment, which is really nice. And it is really important to monitor it because you will see some improvements also of the learning. And then we also create a new cluster, or if it is there already, it will just use that. And you can always change this code because you see we are using this standard D3. This is with the CPU. And we are going to use this for the ray head. And it is good enough for now to go with one node. You can change it if you want, if you plan to run more than one experiment on this compute. Right. So the cluster is created, or it was already existing, and then it's using it. And then here, we're going to use a customized Docker image where all the necessary software and Python packages are installed. And now the configuration for the training run is defined with the environment class. And there is something interesting as well. What I want to do is that every iteration should be recorded and the video should be generated from it. This means that every time the training is finished with one iteration, it will generate a video for us so we can review every step, how the agents behaved. This is really cool, and to make this happen, we want to set the interpreter path as well there. Okay, so for training, we're gonna use this multi-agent deep deterministic policy gradient, or it's called MADDPG algorithm. And as the name suggests, it will be able to train many agents in the same time. According to this code here, if the training runs over 3 hours, it will automatically stop. And also, if the final reward is -400, then it's also going to stop. So we also want to initialize the reinforcement learning estimator. And we're going to use some specific parameters here. Where are the training files or the necessary files for the training that can be found in this source directory that I just shown you before. You want an entry script. This is basically the main script, the main training script that's going to be used from the files folder. Then we also have some script parameters. This is what's passed to the main script at run when it is called. Then we also specify the compute target, what is the environment we want to use, and how long the training should run. You are welcome to change the final reward parameter if you want to get a better result. This is just a good enough result what I have here, but you can also change it. Just remember that if you want to change this, the training will maybe take longer because of the reward it tries to reach. Okay, so that I mean that you might have to update this also, otherwise it won't reach the required reward. So what I also want to know is that I want to see some details about my experiment while it's running. So a button also shown over here says view run details. And if we go there, it will take me to the experiment page of the Azure Machine Learning workspace. And as you can see, it's really cool stuff because you're basically navigating around inside the workspace. So it's really easy to just go ahead and play with it. We can see how long did it take, and we also can see whether there were any child runs and whether it completed and so on. I also would like to show this to you guys because it's really cool. If you go to the outputs and logs, and try to find this driver log. And when it is loaded, you can go through on each and every steps. Now this is starting. The particle scenario is started. Now the first iteration, the reward is -600 whatever. And if you go ahead, it is changing and going a bit lower or higher. It's changing around. Just like it does when you try to learn a new word, right? If you practice it a lot, then it goes better. And later on, it goes up to 400, which is pretty cool. That's one thing. And if you go to the logs folder, you can find the videos as well that are generated. The problem is that you cannot really watch it in here, but you are welcome to download it. So if you download it, and when it is downloaded, you can take a look at this moment, at this step, how your agents behaved. And you should see they don't really know what they're doing yet. But if you would take a look at the video from later on, then you should see that they became maybe a bit better. But just for fun, let's see, because we have a lot of videos and just one of them I touched to see whether it is a bit better now. And yes, look, they go on their landmarks and they try not to collide over there. Pretty good. Okay, so this is what you can see after the run. But what happens when you're actually running your code? So while this is running, you can start up this code here, because evaluation is really important. And what you can do here is that you can also monitor the trials via the tensor board in runtime. And this code basically returns a URL. And if you go there, you will see some dashboards. And you can see how did it go from each and every iteration. You can see all the details. You have a lot of different graphs that tells you information that you can use up for improving your code when you need to do that. And this all happens live while this is running. It's really awesome. All right, the other thing we could do is that thanks to this code, you can download the generated videos inside this notebook. And if you run this code right after you started the training, it is very important, because then it is able to show you the videos in runtime. So now it is showing the last video, but if you watch this run while it is running, the video is always re-downloaded, and then it is showing always the newest, the latest version of the learning. Okay, cool. Now I'm going to switch back to my slides, because I think it is really important to tell you also that this is an open source code. So we welcome your contributions, and if you have any issues or you have any feedback, feel free to reach out to me, to us, or whoever you can reach in the MVP community. And please go ahead and read some extra information at different articles. I pasted here some videos as well. And don't forget to check out the reinforcement learning samples. And I just head back here for a moment because I wanted to show you. Here on these Azure Machine Learning notebooks, you can find how to use Azure Machine Learning. And then inside the reinforcement learning, this multi-agent particle environment is already available. So you can go ahead and try it out. And if you get stuck, you're welcome to find my blog, and you can read about it a bit in detail, how you can do stuff. I keep updating this post as well, so you should see always the latest information there. And if you have any issues, feel free to contact me. So I think that's it from me. So thank you a lot for your time. I hope it was cool. So where is Sammy again?
I don't know. We've lost him. Is he still there?
All right. So we just wait for a second for him. Yeah. So I'm open for questions until then, if there is any. I'll just check out if we have any questions.
I'm back. My net was gone.
It's all right. I was trying to find out if we have any questions.
Yeah, well, if you have any questions, please don't hesitate to ask them in YouTube chat or on Twitch or on Facebook. I have one question I would like to ask. Let's say you want to start learning about reinforcement learning. Where do you start?
So I will start with Microsoft. We have a lot of blogs and all that I shared just previously on my slides. I'm not sure where can we share these URLs, because we have a lot of articles, a lot of documentations, videos, how these are working, especially about the single agent scenario, because that has been released, that build. So that is that there is a lot more a lot more information and a lot more practical info available.
Okay.
Since
So if people want to go back, cool. So if people want to go back to those URLs, you can go back and on YouTube, you can still watch this video again, and you can just forward to this part. It's at the end of the video. So
yeah, we can have them in the comments as well.
Or they can go to my blog post.
Or your blog post. So, and I can add them into the description of YouTube also. So I'll add them there also.
Because there I wrote down all the resources we have.
Cool. There's no questions coming in. So I would say, Eve and Alan, thank you very much for your time to do this special based only on reinforcement learning. I learned a lot. I didn't even know about this Paidia project. Very new for me. But I don't know where the name comes, Paidia. It's quite a hard name to pronounce even.
I can't remember where did it come from. It was that, they were like trying to call it in a name that is just cool. And Paidia, like P-A-I-D-I, right? It's like...
Okay.
I think it's cool. It has AI in it, so it's cool.
Actually, we had in the end of May, we had an AI talk by an associate professor of the University of Alberta. He's called Matthew Gusgiel, and he talked about AI that generates games. So it's a bit the other way around.
Nice.
So it's also very interesting. I will put the link to that video also in the chat. So for people who would like to watch, they can just click on the link and see it. It's a very interesting talk and a good speaker. So
cool,
nothing else comes in. So Eve, thank you very much. Alan, thank you very much for your talks. And we hope to see you soon again. But of course, we had the second AI talk today already. We have another one next week with Ali Mustafa, who will talk about tackling bias and machine learning using crowdsource. But not only that, we still want to promote our bigger event on the 7th and 8th of October. Well, okay. Our Global AI Virtual, 36 hours of AI talks. So we will travel through the whole world and every time zone. And our call for papers or speakers is still open. You can register for the event so you stay up to date with the latest information on globalai.live. So with that, thank you all very much for watching this, and I hope to see you next time. Bye-bye.
Bye, thank you.
Hey, my name's Akansha Malik, and I'm from Melbourne.
Excellent Sami in Belgium.
Hi, I'm Alan Smith.
Hi, I'm Amy.
Amy, Neighbor Test. I come from Spain.
I'm Prasant from California. 大家好，我是卢建辉
Lunar Lander.
I'm Fagazin from Australia.
Hi, I'm Jennifer Marsman from the United States.
Hi, I'm Laerdal from India.
Hi, I'm Matthew Renton from the USA.
I'm Joe Spizak from California. Hi, ismini Ali Daoud from Africa.
Hi, I'm Ana Famana.
Merhaba, ben Türkiye'den Daron Yönder.
Hi.
Hi.